Okay, cool. Hello, everyone. I'm very excited to see all of you. It's Tony from PingCAP. So I'll be the online host today, and Li Quan will be the on-site host. Hello, Li Quan. Okay,
Hello.
so yeah. Okay, so database and streaming systems are crucial infrastructure for lots of companies. Today we'll introduce two great products and how they work together. So in the first half of the talk, we will introduce you a streaming system. Li Quan, I think you are quite familiar with the streaming system, is that right?
Yes. I've been working on this streaming system in several countries. I have questions about this. How many of you have used Apache Kafka before? Or have you heard about Apache Kafka? So a few of them, right? What are the pain points do you think we use it? Apache Kafka. I can answer that. So I've been developing streaming system and we rely heavily on Kafka. I think one challenge when we are working with Kafka is that we need more capacity of Kafka, and we need to work with the Kafka team to provide more capacity. But I think one challenge of Kafka is that when they add more capacity, they do need to manually move the data to the newly added server in order to actually have Kafka serve more traffic. And that process typically takes a couple of days, even a couple of weeks. So which definitely impact our capability to innovate. So I think fast scalability is especially something involved from Kafka. I think this is also one benefit of using Pulsar. So I think that is one thing I want to share with the audience. So hopefully, like Sijie can talk more about the design and implementation of Pulsar to demonstrate the benefits of Pulsar with Kafka. Okay.
Yep. Okay.
Okay. Sijie,
Okay.
Yeah.
Yep. Okay.
Yeah, I'll take over.
Yeah.
So let me see.
Yeah. It's okay. We can see the screen.
Okay. So thank you everyone for coming. I'm going to kind of share a presentation around Pulsar. Pulsar, in a short sentence, is a streaming data platform for modern event-driven applications. And just a little bit back, brief introduction of myself. So I'm one of the founders and CEO of Stream Native. Stream Native is the company kind of founded by the original creators of Pulsar. So we are supporting in making Pulsar. I'm also one of the PMC member of Pulsar and PMC chair of Bookkeeper. Bookkeeper is a storage engine that is used by Pulsar for storing all the national data. And I'm before that I was kind of work at Yahoo at Twitter before, kind of in the machine streaming space for around more than 10 years. So kind of I want to just do the quick test to see like how many people heard about Pulsar before. It's all our like my PingCAP friends. Yeah. So in the short sentence to kind of describe Pulsar, Pulsar is one of the fastest growing project in the streaming space. So if you just we're actually using the product called OSS inside, and then is the product powered by like TiDB. So this is just an example to show like the growth rate for this project. It's also a project ranked as a top 5 Apache Software Foundation project based on the engagement. Have around more than I would say 560 contributors, comprised of 7,000 Slack members. It was doubled last year. The core Pulsar GitHub repository, it has around more than 10,000 commits. It's also growing year over year. Global wide, we have thousands of organizations are using Pulsar production. And this has been kind of, Pulsar has been kind of widely adopted by like thousands of companies across the globe. This is just a snapshot of the current adoption. It has been used by a lot of mission-critical environment. For example, Tencent, one of the largest internet company in China, is using Pulsar for building its billing platform. So if you are a WeChat user, you're sending your friend lucky money, and that lucky money will go through Pulsar first. DD is using Pulsar for supporting for building its real-time customer experience for its passengers and drivers. Companies like Intuit, Verizon, Yahoo Japan, Flickr, they are all using Pulsar for building their company-wide mainstream streaming platform. But those are kind of just facts talking about Pulsar, but what exactly is Pulsar? So in short, it's a kind of a cloud-native streaming data platform for event-driven applications. So if you use Kafka before, or if you have been using mainstream queuing solutions like RabbitMQ, ActiveMQ, NUTS, like SQS, you can simply think about Pulsar as a superset of both RabbitMQ and Kafka. But what exactly what I'm talking here is about what does the cloud native streaming data platform mean? So we have to kind of dive deeper into the first term is it's a cloud native system. And what does that exactly mean? If you're familiar with Kafka, Kafka is a simple kind of distributed kind of broker system. So all the functionality are comprised into a component called broker. And that broker is used for both serving the PubSub request and as well as storing the data. The way how Pulsar is doing differently from Kafka or the other mainstream system is it introduced a concept called, it's using a compute and storage separation architecture. It divided the entire architecture into two layers. One is the broker layer, the other one is the cookie layer. So the broker layer is essentially the serving layer. It's all your kind of Pulsar clients are connecting to the broker for producing the master and consuming the masters. And the storage layer is used for serving storage the data and keeping the data around for like a user requested retention period. And with this computing storage kind of separation architecture, it allows you to scaling up and scaling down quickly without rebalance the data. So one of the major pain points that you might be facing using Kafka is when you're scaling up, you need to copy the data around and moving data from one broker to the other broker. If you have a large cluster storing hundreds of petabytes of data, the operation, the time to rebalance data can take a couple hours or even a days. But by breaking down the compute and storage, separating them into the individual layers, you don't need to rebalance data when you're scaling up. And this allows you to leverage the power from Kubernetes. You can write any scheduling operators that is able to scaling up, scaling down based on the utilization in traffic. And the other benefits coming out from this compute and storage separation is that there's no single failure of the no single failure of point is the no single point of failure. Sorry. And if there's a broker being down because broker doesn't store the data, so the ownership of a partition can quickly shift to the other brokers. So the recovery time is usually done within dozens of milliseconds. So you wouldn't notice the changes there. And because the data is stored in the storage layer with multiple replicas. So if there's a storage node down, the producer and the consumer will not notice that the changes is because they're interacting with the broker. and broker can identify there's a bookie down and change, replace the bookie with a healthy bookie and continue work there. The third benefits coming out from this compute and storage separation is that you can use a lot of like cloud native object storage like S3, GCS, Azure Blob Store, even in on-prem environment, you can use HTAP as a tier storage. And Pulsar would handle the automatically tiering between the bookkeeper and the tier storage. So all these are done in a transparent way. With these benefits is that you can keep the data for much longer duration without expensive storage cost. Besides that, there's also other kind of enterprise features like multi-tenancy geolocation, which I'm not going to dive deeper into individual kind of features. If you're interested in Pulsar, happy to dive kind of talk after the meetup, or I can share Pulsar website, and there's a lot of information there. One last thing I want to emphasize here is the by adopting a cloud native architecture, bringing a lot of benefits around kind of scalability, reliability, and availability. And that's what we call Pulsar as a cloud native system.
Excuse me. Can I ask a question, or you want to put it aside?
Yes, you can ask a question now.
Okay.
Yeah.
Right. I want to ask a question. So first question is about like we know like there's definitely enough benefit from the architecture of the computation storage separation. That's definitely true. But how will like the network traffic, you know, because some reason there's like a lot of, even because it's just like it's streaming, right? There's a lot of data running around on the air. So definitely they will, you know, search or even get more pressure on your, network things issues.
Yeah. So I think you definitely bring a really good kind of a topic here is about network traffic. So I think there's a misconception that people usually would have when talking about compute and storage separation is if you're talking about a system without data replication, then if you're just using a Kafka-like system, then your client just talk to the broker, and because there's no replication, so there's additional network. So the only network interaction is between the clients and the broker side. But if you're talking about high availability, introducing replication factor of 3, then meaning besides you talk to the broker, you will also have 2 additional networking hubs from the leader to the master. So to the leader to the from the leader to the follower. So the additional networking is you cannot avoid the networking additional networking hubs if you want to gain high availability. So by turning that into kind of the current setup in like a Pulsar's architecture, if you so in Pulsar, there's actually a concept called non-persistent versus persistent topic. For non-persistent topic, it will just all the traffic will just go through broker. It doesn't persist the data the storage there. So it will just produce the data to broker. Broker dispatch the data directly to the consumer side. But if it goes to persistent topic, then you will see additional hub between the broker and the storage. But the broker and the storage, if you count this producer to broker as one, the first network hub, the broker to the bookie as the second additional hub. So if you count the total number of the network hub, it would be exactly same with Kafka with the leader follower replication mechanism.
Even so, I will say like even in the Kafka itself, we still have the problem like this, right? So it's just like intrinsic issues between if you want to use the computation storage separation. But I mean, there's a question that and rationale like, okay, well, if you calculate the total numbers of the jump or the router hub, that would be no such big difference. But again, like I'm really curious about you can just take it later off the road. Yeah. But that's basically I'm just curious like how you handle if the data is really huge, like is that a problem? Because even in like OLTP, like ARA or some other things, that will be a problem.
Yeah,
the network will be a problem. That's what I think. So thank you for your. I think this is still like a good answer, a question answer. So
yeah.
Thank you for that.
Sure, happy to discuss more about deeper after the
All right.
presentation. So moving to kind of second piece is that for this sentence is that cloud native is from architecture perspective is a huge difference between like differentiating Pulsar from the other system. The other part is more like what we call it's a data streaming data platform for event-driven applications. And what does that exactly mean is that when we're looking into the entire enterprise architecture, usually it will be kind of largely divided into domain. One is the application domain, and the other one is the data domain. So in the application domain, you will be running a lot of microservices, event-driven applications. Those are mission-critical, user-facing, direct revenue impact applications. They are connecting with each other through a mastering system for reliable asynchronous communication. In contrast, on the other side is the data domain. There's a bunch of the data, real-time data pipelines running there, moving data from place to place. So when we're looking into the enterprise architecture, you usually see like a streaming system like Kafka Kinesis is being used in the data domain side, while traditional mastering queuing solutions like RabbitMQ, ActiveMQ, and as well as some of the legacy commercial products like Solar's typical IBM MQ, those are kind of common mastering queue solution in the application domain. While Pulsar is designed in a way that is able to cover both the application domain and data domain, but we found like Pulsar is actually a much better fit in the application domain, we found a lot of Pulsar's adapters are actually using Pulsar in the application domain for supporting mission critical business applications. And so when we get, I'll just use an example to kind of e-commerce example to kind of describe on the business application that you might have in the application domain. This is just a very simplified diagram in terms of how it looks like. Usually you will get started with, from the left side, you will have a set of front-end services. Those front-end services will take the request coming from the user side. Let's say this is an order request. You would be kind of sending the order request by publishing the request into a topic. And this topic would kind of used for accumulating bunch of the order requests. And the back-end service will just consume those order requests and process those orders. And you might be doing like a kind of reserve the order, or talking to the payment services for processing the payments, and talking to the delivery services for scheduling the delivery for that order. So there were a bunch of the back-end services would process those orders. And once the order is being processed, they would kind of update order status topic to reflect what is the current status of the orders. And those orders order status might be used by the front-end service to display what is the current status of those orders. So you might be looking into some sort of table view that is able to kind of view the orders, the status of those orders. And once you have both the request topics in the status topic in a system, you might want to connect those data with your kind of analytics platform for analytics services for analysis the certain patterns are doing forecasting about those orders. So this is kind of a very typical business application setup, but it's obviously simplified a lot. So that means when you're building a kind of event-driven applications, and the question is really coming down what is the right data abstraction that we should offer to the users, what is the right API to provide, and is it just the stream, or is also other the other APIs? What are the primitives to provide, and what how to meet business requirements, and what kind of tools that we need to offer? And I think that is how we differentiate Pulsar from the other system in terms of how we handle the modern event-driven applications. So when we get started kind of really looking into this modern event-driven application, it comes down to 5 fundamentals. The first one is usually get started with data abstraction. And in terms of data abstraction, is Pulsar essentially is a pub subsystem. So it's used for asynchronously broadcast message to a set of consumers, and it mainly used for decouple the producer from consumers. And the subscriber state is essentially managed by the system. One thing I want to call out in terms of the data abstraction is the fundamental is a pub sub. We store 1 copy of data, but the difference here is it provides a flexible subscription model. It allows different applications to consume the data in different consumption model. In Pulsar, there are kind of 4 consumption model being supported: exclusive, failover, share, and key share. If you're looking into like in order consumption, exclusive, and failover, and key share will meet their requirements. But if you don't look, if you don't care about the ordering, more looking into scaling up the consumption, shared and key share would also be a good kind of consumption model. But fundamental of this within this pub sub foundation is definitely a replayable streams, meaning the data can keep in a stream in infinity time, because with the tier storage you are able Pulsar is able to offload the data to cheap storage like S3 and keep data for much longer time. And this infinity retention would make the data in those streams become the source of truth, and you can read the data from any position. And eventually, those events in the streams can be stored in either raw format or columnar format. Pulsar is integrating with Lakehouse as its storage format. So the data can easily be uploaded into Lakehouse being stored as a columnar format. So with this foundation, you have this replayable stream as your topics for the data abstraction. But at the end of the day, when we expose the API to the users, besides this flexibility of consumption model, essentially allow you to support both the traditional messaging and as well as the streaming use cases. So what you can get out of this flexible subscription model is, first is a stream. You are able to consume the events in order, exactly what you can get from Kafka. And second is this stream can be modeled as a queue, which is a fundamental decoupling mechanism used in a lot in the traditional messaging queuing workload. And the queue essentially is the unit to distribute work across a set of workers, and which is typically you can find in the event-driven applications. And besides that, there's a couple kind of queuing-oriented features such as round-robin routing, fatigue-based routing, individual message tracking, and delivery delay or scheduled delivery are all being exposed as part of the queue-based subscription. And the last thing is, once you have a stream, this stream usually store all the changes of the data. And in certain use cases, you want to view the data in the topic as a table, and you want to access the last value for individual message keys, where the in Kafka, there's a concept called compact topic. In Pulsar, we have a similar idea there. It's more what we call a table view. So in other words, you can view a stream as a table, and you can access the latest value for each master key. And this can be very useful for sharing states between different processes. You can use it as a kind of distributed cache with local reads. And definitely it also integrates well with the Pulsar transaction. So you can make sure the producing to a topic that can be viewed as an atomic change to the master key. The last thing we have the topic, we have the abstraction, then there's a bunch of primitives that the Pulsar offer to support building the application. Things like in the PubSub model, usually you have a shared producer and shared subscription model. In addition to those models, we're also introducing exclusive producer and exclusive subscription that is allowed you building applications that require like a single leader type of applications. Once we have the share and exclusive primitives, then Pulsar also kind of offer additional semantics that including those traditional messaging deliveries are semantic, including at least the ones, and most ones, and exactly ones. So all supported for meeting different business requirements for building the application. And I'm not going into details, but lastly, all these abstraction API and primitives are actually bundled together and offer into 3 layers. Well, the first layer is the client. And the client you can think about is a single high performance TCP protocol, and that protocol is versioned and maintain backward compatibility. So, and the protocol is being implemented using different languages. Right now we have Java, Go, C, C#, Python, Node.js, so you can build application using different clients. But sometimes you're not able to implement all the clients in different languages. We also provide a simplified HTTP-based API, so you can issue like admin request through the Pulsar admin portal, and you can also produce and ingest using the HTTP request. But sometimes using client to give you all the flexibility, but sometimes you also need to write a lot of code. On top of client, we also provide a simple serverless event processing framework called function. This allows you just focus on writing the application using functions. And on top of function, we recently also introduced a circle layer that is designed to simplify building the application, including logic on doing filtering, transformation, and routing. So with all these 3 different tiers, it actually gives people a flexibility to build different type of applications using the tools. So I think to kind of conclude my talk here is that also as in the application domain, usually it's usually a kind of complicated event-driven application, and it's not just simple streaming abstraction or streaming API. It requires a wide range of abstraction and API and semantic for each specific problem. And Pulsar is the system that is designed using the cloud-native architecture and providing the right abstraction and API to help solve the event-driven application problems in the most kind of a nature and comprehensive way. So that's kind of my presentation around Pulsar.
Okay, cool. So yeah, we also have 3 questions online. So you can go to the Zoom and Q&A session. So I'll read those questions. The first one is, could you also talk about TTL on tide storage?
So good question. Actually, let me go back to the. So on tier storage side, so there's two concepts. One is called TTL, the other one is called retention. Retention is how long you keep the data in the system. So you can configure the retention set. I want to keep the data for a year, and then it will retain data for a year. And TTL is a concept more or less on the subscription side, meaning if a consumer doesn't consume the data within a time range, then this master would automatically mark as consumed. So in other words, it would be hide from a given subscription, but the data is still there. So you have the flexibility to say, I have an application that I don't care about the data. If the data is older than like 3 minutes, so then you can configure the TTL to be 3 minutes. And after that, if the consumer doesn't consume the data within 3 minutes, then it would just skip those data. But the actual data is still there because some of the other application might still want to consume the data. So the TTL concept is more tied on the subscription side. The retention is tied to the actual data side. So you can use that to control the lifetime of the masters within your system. And that applied. It doesn't really matter the data is in bookkeeper or in tier storage.
Okay, cool. Thanks, Sijie. So another question is, so is S3 and blob storage, are those code storage?
More or less. So in terms of cold storage, meaning they are kind of old data, because from streaming data perspective is that usually you ingest data coming in and the data quickly will become old, and those old data will be moved to the tier storage. However, in certain application, they might want to replay the data. So when they replay the data, one thing I want to call out is the broker will read directly from the tier storage. They will not. We don't need to get the bookkeeper to load the data from tier storage and insert the data again. The broker will just go directly to the storage side. So it's a cold data, but you still are able to access the data and access the data in a very hash-proof way.
Yeah, okay, cool. The last question would be, so how do you account for consumers who are offline that missed those messages?
Yeah, so the how do you account for the consumer? Okay, so for each topic, you will have a bunch of different subscriptions associated with the topic. The subscription will keep a subscription state. The subscription state is maintained in the system, and the subscription state will describe like what our messages has been consumed and what our message has been acknowledged and what our message is able to kind of delete. So if you have a consumer coming offline, it's totally fine because the data will be still there. There's a subscription state will record the consumption state, and so when the consumer come back online, they will resume from the last kind of the save point from where it left.
Okay, cool. Thank you so much, Sijie. So I believe from his talk, everyone now knows a lot about Apache Pulsar. So in the second half of the talk, we will introduce you TiDB. TiDB is a distributed relational database with HTAP architecture. I'm now introducing you Li Shen. He is the SVP of PingCAP and one of the earliest employee of the company. He knows TiDB extremely well. Let's welcome Li Shen.
Okay, thanks, Chenhao. Yeah, I'm the next speaker. Yeah, for this talk, it's not a quite comprehensive explanation about TiDB, just a brief introduction. Then I will show you a demo that how TiDB can work together with other systems like Pulsar to build some real-time stream events application. Yeah. So first, what about PingCAP? PingCAP is a company behind TiDB, and we provide the enterprise level and cloud-based service of TiDB, and we have team globally and also backed by the global investors. And TiDB is our main product. It's a NewSQL database that is distributed and provide both transactional and analytical processing ability. And it's built for the cloud to power the modern application. Yeah, there's mainly two types of use cases. First is for the transactional workload, you can use TiDB to get scalability and also high availability, like some mission critical scenarios, payment, transaction processing, wallet, or inventory management, metadata storage. Yeah, you can get much larger, you can get a scalable relational database to support your growth. Yeah, and also it's MySQL compatible. So if you are using MySQL, it's very easy to migrate from your existing database to TiDB to handle much larger data volume or traffic. Yeah. And the second type of use cases would be, we name it real-time HTAP workload. For TiDB, we can handle both transaction and analytical workload. You can run some complex query on top of your fetch data. Yeah, you can use, so that's called HTAP. The typical use cases would be real-time dashboard or real-time anti-fraud or data as a service. Yeah, so that's two types of use cases for TiDB. And I can see a lot of companies adopt TiDB because of those reasons. As I mentioned, to scale the existing relational database to support the business growth. Yeah, growth is very important for the business. And if you want to build a modern application on top of a bunch of data, yeah, it's not easy for the legacy database to handle large amount of data. And TiDB can help you both handle the data volume and also the query complexity. Yeah, you can build more, you can run more queries on TiDB. Yeah. And the next one would be you want to adopt the cloud native architecture. I think this also shares something same with Pulsar. We have cloud native architecture. You can easily run TiDB in Kubernetes or on public cloud. Yeah, and we also offer a TiDB cloud, the managed service on public cloud. So it's very easy for the enterprises to adopt TiDB. Yeah, and we also see that some large enterprise use TiDB to build their private database as service platform to handle their business growth. Yeah. The last one would be cost saving. Yeah, actually, we saw several companies adopt TiDB and not only support their business growth, but also get a lot of cost reduction. Like, for example, in our last meetup, Pinterest engineer mentioned that they adopt TiDB to replace HBase, and they save a lot of cost. It's up to around 80% of their hardware cost. Yeah. So that's a few initiatives that drive the adoption of TiDB. And I mentioned these words quite a few times, growth. I think one of the key benefit of TiDB is that we can support your growth, the growth of your business. The growth is a happy problem. For the business part, would be happy. The business owner would be happy if you have more and more customer, more and more data. Yeah, they make more money. Yeah, but for the CTO or technical owner, it would be a problem. You need to handle much larger data volume or much complex situation. Yeah, especially for the infra team. It's not easy to scale your infra. So I think that's why we can see more and more infrastructure software focus on provide the features like easy to scale. Yeah, TiDB and Pulsar share something common in this area. This is a high-level architecture of TiDB, and there's a few more good content on website or on YouTube. Introduce the detail of architecture. Yeah, I will just introduce a little bit here. Yeah, we have for the TiDB database cluster, we have three key components. On the left side, the red one is a SQL layer, handle the MySQL protocol and connection with the client or application. And the top one, the gray guys, is PD, is metadata storage for the cluster, and also keep the workload balance in the whole database cluster. And the right one, the yellow one, the storage engine layer, they are the nodes, the instances that store the actual data. And for TiDB, we have two kinds of storage engine. One is row-based storage engine, another is column storage engine. So, but you do not need to worry about that. The database will handle it for you. You do not need to worry about which storage engine to choose. Yeah, our smart optimizer will choose it for you. Yeah, that's what we call hybrid transactional and analytical processing. Yeah, so to scale, for the computing layer is easy. You just need to add more nodes there. It's easy to scale the computing layer, the SQL layer, but for the storage layer, it's not easy to scale it. There's some work to do there, but the TiDB will do everything for you. You just need to add more nodes here. For example, if there's one node, you have too much data there, and if you want to migrate some data to other nodes, or both data volume or the traffic, you just need to add a new node to the cluster. Then the storage engine, storage cluster, and also PD will discover this situation, the unbalanced situation, and use some command to move data from the overloaded node to the new added node. Yeah, so you do not need to do the things like resharding or manual rescaling. The cluster will handle it for you. It's easy to put like terabytes or even hundreds of terabytes data in single cluster. Yeah, for the largest part, one of the largest production TiDB cluster, we have there is a table has three trillion rows in single table. Yeah, yeah. So it's easy to scale. Yeah. Okay. So that's the TiDB kernel, and besides the kernel, actually there's if you want to use TiDB for your application, database kernel is not enough. You need to put TiDB, the database, in your whole ecosystem. Yeah, like run TiDB in cloud, on public cloud, or in your own private cloud. Yeah, so since it's an open source database and it's cloud native, you can run it anywhere. And also, we provide quite rich ecosystem tools like backup restore, CDC, data migration, yeah, to help you to operate your database. And we also have quite great integration with the whole ecosystem, like Spark, Datadog, Flink, or also the streaming computing product like Kafka and Pulsar. Yeah, we have several production use cases that our customer use TiDB with Pulsar together. Yeah, so here we build a demo with TiDB and Pulsar together to give you guys more sense about how to use it. Yeah, it's not quite it's a simple demo. First, if use Pulsar and TiDB together, there's two ways. There's two things you can use. First one is that TiDB can be used as a sink of Pulsar. You can ingest data. You can use Pulsar as like MySQL and ingest data from that queue to TiDB. because TiDB has support MySQL protocol, so it's easy to build something to ingest data from Pulsar to TiDB. And the second way is use Pulsar as a sink of TiDB. TiDB has a tool named CDC. CDC stands for the change data capture. It's similar with with the binlog of MySQL. Yeah, you can capture the data change. Then we have a driver connector between CDC and Pulsar, so it's easy to ingest our change log, change feed to Pulsar. Yeah, so with this you can connect TiDB with other systems. Yeah, and for the demo, actually we have two demos. The basic one is OSS Insight. For the OSS stand for the open source software, and inside, you can get. We would like to get more insight about the open source world. Yeah, we will introduce a little bit. We grab the GitHub event data from GitHub with its API and ingest the data in real time to TiDB. For here you can see there is around 5 billion billion rows there in single TiDB cluster, and based on those data, we build some dashboard report to give you more sense or insight about the current open source world. Like here is a ranking of the repos. That the ranking is based on some metrics like star number or PR number. Yeah, so it's the report is on fresh data. Yeah, and you can also besides the whole view of the open source world, you can also dive into some repos. For example, like Pulsar, you can see here. Yeah, you can see some basic information about Pulsar, and you also can see some advanced features like the distribution of dark adders or the distribution of the PR, the contributors. Like you can see through native Tencent. I think Sijie mentioned Tencent. Yeah, so you can see the more advanced insights for the open source world. Yeah, so it's quite. Actually, at the beginning, it's a tool for ourselves. We want to operate the open source community better, but we found that it's also useful for a lot of people. So we build a public tool based on our product, TiDB. So it's also a good tool to demonstrate the capability of TiDB, the real-time HTAP capability. Yeah. So this is a basic version of the demo, and you can see here is we use TiDB to store data and also run some real-time batch queries to generate a real-time report. Yeah, but we got some requirements that whether we can provide more real-time features, like what is happening in the previous maybe 5 minutes in the open source world. So we built more real-time demo based on this one. It's a live.osinsight.io. Here you can see there are more real-time features. Like here you can see the change data. That's real-time data from GitHub API, and you can run some filters here. Like you only care about the JavaScript word. You can add some features here, or with some filter for the keywords, and you can see those numbers are jumping. So those are real-time counters. So for those features, it's not easy to build those features with the database. So that's a streaming computing problem. So that's the motivation why we like to introduce Pulsar to this application. Yeah, and we one thing I would like to show here is we have quite a fancy demo here. Yeah, here is more fancy diagram that you can see how, like connect the real world and the open source world together. Yeah, so it's an interesting demo. You can take a look. Yeah.
Great. So I do have a question regarding. Sorry.
Yeah, there's two sides. Yeah. So as I mentioned, we're based on the basic demo, we would like have some quite advanced feature that would need a streaming processing system. So that's the first motivation we want to choose Pulsar. We need both MySQL and also streaming processing. Yeah. And the second one is that, as I mentioned, TiDB is a database that can scale to support hyperscale data volume or traffic for our. I have seen like in single database, there is millions, 1 million QPS. Yeah, so it's a super big cluster. So I think for Pulsar, Pulsar has quite good performance. You mentioned the performance comparison benchmark. Yeah, we in our investigation we saw this benchmark from Native. It's quite impressive. So it has better performance and very easy to scale. You do not need to do the manual things to scale your streaming system. It's easy to use. So we share something common. So that's another thing. Another reason why we choose Pulsar. Yeah, the last one is that both TiDB and Pulsar I think is proved by the production, and we are confident that we can use those products in the mission critical services. Yeah. So here is the current architecture of how the OS Inside demo use Pulsar. Before the live demo, we ingest data directly from GitHub API to TiDB, to the database. It's simple, but it's not convenience. So here we introduce Pulsar and ingest data in Pulsar first, then consume data there, ingest to TiDB. So that's the MySQL part. Then some of the query would go direct to Pulsar for the real-time streaming processing, like the real-time counters, the real-time events. So that's how we use Pulsar. And we also provide, like I mentioned, connectors of TiCDC with Pulsar. So you can use TiDB with Pulsar together for your production. Yeah. Yeah, that's my sharing. Thanks.
Thank you. I actually have a question for both of you guys. The same question. So I think in CJ's presentation, I think that the takeaway is that with Pulsar, it's very easy to build events streaming applications, right?
Yeah.
And I think in this presentation, I think it's pretty easy for users to build like modern data applications. Why do you think these two can work together very well? Why I ask this, because I do have some personal real-world experience building those applications, even streaming applications. They are definitely something I think that they can work better to really like make the whole thing end-to-end, work end-to-end. In CJ's presentation, you mentioned that you have table views, right, to serve those traffic in different services within your front-end service and back-end service. So do you think that Pulsar can be the end-to-end solution for that part, or you can integrate with other solutions?
No, I think that from my view is any kind of business application, the architecture itself is very complicated, but you can definitely divide those business application into a couple of parts. Is more on ingestion, data ingestion, reliable data communication, data serving. And I think what Pulsar play well is definitely on the data ingestion / asynchronous communication side. And what I think TiDB play very well in the data serving side. And by combining Pulsar and TiDB together is actually it will become a modern stack for building, I would say, real-time data applications. That's kind of my view, but I would let
Yes, Sijie has a great answer. I share the same opinion with Sijie. Actually, no product can solve all the problems. Yeah, and it's a need a better architecture to do this. And but I think for the modern infrastructure software, one key feature that is composable. It could be work together with other systems with a standard API, then build the whole system. And another thing is that if you are choosing considering the architecture for the different components, I think if there is an unmatched capability, for example, like you choose the TiDB for your primary database, and you output the ingest the change feed to the downstream system. If the TiDB cluster has a quite heavy write workload, but the downstream cannot handle that scale, that could cause some issue for you. So that's why I say the matched capability of the composed software, that's important. Yeah.
Okay, sure. I think the second question from mine goes to Sijie. I think, in my opinion, the best kind of like I think event streaming architecture is extremely good for if you want to do some stats on the event time, handling the like arrival states. And I think this is really good. So maybe could you share maybe some real world example that streaming event architecture can be kind of like add a lot of value to the customers?
Yeah, so I think the kind of what we have been typical seeing in companies like MarTech, healthcare, usually you would end up building a lot of workflow. Like meaning workflow is like, for example, if you go to DoorDash, when you put down an order, then after you go put down an order, essentially trigger a workflow for that order, because it needs to find the driver, and the driver need to go to restaurant and pick up the food and then deliver the food. So all of these getting into a workflow, and the workflow essentially is connecting with different microservices, and that is a very typical, was a common pattern that you will see in both MarTech, sometimes and also in retail, e-commerce, and as well as in healthcare, because like I would say a lot of companies eventually became a very complicated giant application, and you need different type of system to connecting together to serving that business.
Yeah, I also want to say that event basically from the technical point of view, you have order of event arriving, but you also have a timestamp indicating when the event is generated.
Yeah.
And this workload is really good for kind of really well for streaming system because it's windowed by the event timestamp. In case of like if you save that data to database, you have to constantly recompute in order to handle those late arrival events. I think which makes event streaming a really good system to work together with to handle all this.
Yeah, I think the database, so a streaming system can only handle that's what is happening.
Yeah.
But it's not able to, it is not designed in a way to handle what has already happened. And databases like TiDB, it's good to handle what has happened.
Yeah.
But with the power that is able to query or kind of get those insights about kind of what happened in real time, and that's the power coming out from TiDB. By combining a system that understands what's happening with a system that is good at understanding what happened, you're actually serving the entire life cycle of the events that are in data that is happening.
Cool. Yeah. So I have a last question. So I think I have been like working with systems, and it worked really well for computing the result. But I have spent actually a lot of time, effort on distributing the result to different systems so that data is available for the application. What are some of your recommendations of doing this? So the distribution of your distributing the result by your streaming system.
Yeah, so I think distributing the result is more or less getting into a serving, but serving is part of kind of distributing the result.
Yeah.
But distributing the result, there's multiple ways to kind of think about distributing result, which I usually see this is kind of ingestion and serving problem again.
Okay.
So ingestion side is that in distributing the result towards a cache, ingest to cache, or ingest to data warehouse, or ingest to repeater basis. And the other one is more or less on the serving side. So streaming system is definitely not designed for serving or distributing the result. And those results, so we can calculate those results in real time, but those results will not be kept around for serving of queryability, and where TiDB will coming in, serving the purpose of receiving those results and serving those results and providing those results in real time, and which also allow people to go back in time as well.
Okay, thank you. I probably take too much time for the questions. I'm wondering if you have any questions from the people attending in person or people attending online.
Okay. Yeah. Thank you very much, Siji and Lee. So we actually have a small gift for both of you. It's a very nice photo. Only the speakers at the PingCAP. Yeah.
I think this may be the most exciting part for me. So we do have a speaker exclusive swag from PingCAP and TiDB. So this is only a gift to people who have delivered tech talk in our Meetup or conferences. So this one goes to Siji.
Thank you.
And people attending person online, if they won't get one of this, just contact us and deliver tech talk. And this goes to Lee.
Yeah, as a buddy owner of this flag, I go like. Okay, thank you.
Thank you for having me. Yeah.
Okay. Thank you everyone very much. So last but not least, if you want to join our community, try out TiDB Cloud and learn TiDB from PingCAP. You can scan these barcodes. Okay. Thanks everyone for joining us today, and see you next time.